So welcome to the weekly colloquium series of the C3.ai Digital Transformation Institute. So as some of you may know, our mission is to promote research at the intersection of AI, cloud computing, machine learning, to digitally transform business, government, and society. The Institute is headquartered at Illinois and Berkeley, and we have, with the generous support from C3.ai and computing support from Microsoft and a number of other universities and industries are our consortium partners. Before I introduce today's speaker, I just want to mention that there are a number of other talks that are planned for the rest of this semester. The next one will be by Stefana Parasco and Corina Tarnita at Princeton, then Stefano Savato at UCLA, Jeff Sharma from Illinois, and Louis Shah from Illinois. Those are the next four, but we'll also have more colloquium talks through the summer and in the fall. So if you want to listen to any of the talks again, or if you want to go back and view the workshops and other symposia that our institute has organized in the past, you can go to our YouTube site, and all of them are recorded and are available there. So here's an example. So for example, there was a workshop on deep learning that Renee Vidal and EMA organized. And so here's a talk from there, and there's other talks here that you can see as examples. So if you go to our YouTube site, you should be able to see everything that we have done so far. So today's talk will be roughly 40 minutes, and there'll be 15 minutes of questions. That's what it's written here, but actually it's going to be slightly different. I encourage you to post your questions, and Nadi has kindly agreed to take questions during his talk. So while the talk is going on, if I see any questions, or if I have a question myself, or if one of the panel members have a question, we will interrupt him and ask the question. So please feel free to put your questions on the Q&A, and I will read it to him. You can upvote questions, and if there are questions that receive a lot of votes, we'll ask them first before we get to other questions. We will try to answer as many questions as time will permit. So today's talk is about understanding deep learning through optimization bias. And we have one of the pioneers of optimization bias and what it means to deep learning giving the talk today. It's Nadi Srebro. So Nadi is interested in statistical and computational aspects of machine learning and the interaction between them. He has done theoretical work on statistical learning theory and algorithms, worked on novel learning models and optimization techniques, and worked on applications in computational biology, text analysis, and collaborative filtering. Before he joined the Toyota Technological Institute in Chicago, Nadi was a postdoc at the University of Toronto and a visiting scientist at IBM Research. I myself have known his work through his remarkable work on optimization bias, which is now being followed by many, many people. And without further ado, I'll let Nadi take over. So Nadi, you can share your screen, and when you're ready, and start, and you can unmute and turn on your video.
Yeah, thank you. Can you hear me?
Yes, we can.
Yeah. Yes, you'd think that after more than a year of this, I would be able to find the unmute button, but I guess I'm a slow learner. Okay, thank you for inviting me. Let me share my screen here. 1 second. Could hopefully find that button here. Great. Oops, wait. Sorry. Okay. It's not letting me.
We can see the screen.
Sweet. Yeah, but I can switch slides. Let me try to see if I can. Okay. Let me try again. Okay, and now you can see the screen again, right? And I think I will
Not
be able
yet.
to...
Oh yeah, now we can see it. Yeah,
Yeah.
we can see it now.
Okay, and you can see it, and I can switch slides. Okay. Maybe I can switch slides. Okay. Thanks. Okay. Thank you. Thanks for inviting me. And I'll I should say first, I feel like I should apologize. I feel a bit embarrassed. I saw that many of the talks in the series have been about using our computational our statistical and computational techniques to combat COVID. And I feel embarrassed that this talk is not going to be about that. It's about half the talks are about that. Which
Don't worry about it. I think other
I
talks,
think it's
there have been
great.
other talks. Yeah,
Right, but I think
talks.
it's great. I think I just want to say I think it's great that many people are really pivoted and started doing that. And I want to encourage anybody that's doing that to continue doing that. What we'll be looking at today, though, is sort of pre-COVID work and looking. It's trying to understand the sort of fundamentals underlying deep learning, and I'll be describing it up a journey that we've been taking the past few years. I think Serkan has alluded to already before. And this is of understanding deep learning through the lens of optimization. And I should say this is a joint work with a lot of co-authors. Mostly I want to mention Behnam Neishabur, my student, former student that really was the one that got me into deep learning. And also Surya Gunsakar and Blake Woodworth that worked in the group, and a lot of the work here, almost all the work here, is due to Surya and or Blake, and also Daniel Sudri and Jason Lee that have been collaborating on this in the past few years. Okay, so let's start, and we're going to be talking about trying to understand deep learning. So from a simplistic perspective, what it is about deep learning, there's nothing really special there. We just have some model family, this model family, or if you think of it as a hypothesis class of, we're going to learn by just taking a model, this deep neural network, and trying to fit it to data. And when we learn by fitting a model to data, there's generally three questions we need to answer. Okay? So we want to understand, what's the capacity of this model class? If we fit it to data, will we be able to generalize to new data? We want to understand, what can this model class represent? Can it actually represent the useful things that we want to represent? Can it approximate reality in a sense? And we have to understand whether we can actually fit it to data efficiently. So when it comes to deep learning or fitting neural nets, then on the surface at least, we actually understand their capacity very well. So we understand how many samples are required for generalization. And roughly speaking, the answer is that the number of samples we need just scales with the number of edges or number of parameters. Okay? So this aspect, and then this is we've known this as a community for several decades now. Okay? And the next question we want to ask is, what is the expressive power of neural networks? What can they capture? Can they really capture reality? And that's the question that usually people focus on when they think of, are neural networks good for learning? Is this a good learning mechanism? And so we have both classic approximation theory results, which tell us that they are very good. They're in a sense universal because with a neural net, we can approximate any function or any continuous function, depending on exactly what your exact definition of approximate is and what your definition of any function. But in some sense, these approximation results are maybe perhaps not the most useful, because it's true that we can approximate any function, but to approximate any function, we need a huge network. We need a network whose size scales exponentially with the dimensionality. And remember that the game here is that we also want to generalize. And since our generalization ability depends on the size of the network, then in order to generalize, we want to make sure the network is not too big, is small. And so it doesn't really help us that we can approximate any function with a huge network. Really, what we want to ask is, what can we approximate? What can we approximate well? What type of realities do neural networks capture? But networks that can generalize, so networks with a small number of units, small number of parameters, small number of edges. And there's been lots of or Connect, and lots of insight about that they really can capture, these networks can capture lots of interesting things. And this is perhaps, again, where most of the work on, or most of the thinking of why are neural networks good has come in. If you go to, for example, somebody working on computer vision that uses neural networks, and I actually can't see who is here today, but I'm assuming that many of you or some of you do work on computer vision or maybe other tasks. And if you, think of why are neural networks good, then usually most of the explanation is, well, neural networks really capture visual phenomena very well because you have low-level features and mid-level features and high-level features, and they really model visual phenomena well. So this type of answer is really saying that a small neural network can approximate very well a visual phenomena, and this is why it's good for learning visual phenomena. I would actually go a step a step beyond that, and say that I actually don't need to understand visual phenomena in order to know that neural networks have great expressive power. Okay, and they are in a sense universal, not so much because of that they approximate any continuous function, because as we said, that's only with a huge network, but even small neural networks are universal. And the fundamental result here is that any function that's efficiently computable, anything that's computable in time t, can be represented with a neural network whose size is roughly proportional to the amount of computation required. So again, it's important to emphasize, this is not the amount of computation required to learn. This is the amount of computation required for the predictor itself. And so I would argue this is basically tells you that they can represent everything, because at least the way I view learning is about being able to find from data a predictor from some tasks. So instead of programming a predictor using a rule-based system, using data and examples to learn this predictor. And if there's no predictor that can be computed efficiently, there is no point in learning the predictor. Okay? So anything I want to learn is definitely can be computed in a reasonable amount of time, and so also can be expressed with a small neural network. So in this sense, neural networks really, we understand very well how neural networks are, in a sense, an ultimate learning machine. Okay? They can express lots of things. In fact, they can express, in some sense, anything we might want to learn. And they can be learned using a reasonable number of samples. Okay? Because we can, small neural networks can express lots of things and can be learned with a reasonable number of samples. The problem here is, of course, when we get to the computation. Okay? And so this result that tells us that neural nets have ultimate expressive power is actually maybe more of a negative result than a positive result, because we know that a class that's so expressive cannot possibly be efficiently learnable unless P is equal to NP, or at least unless cryptography is not possible. And indeed, we have very, very strong negative results about just how hard it is to learn neural networks computationally. Right? So we know that this task of fitting a neural network, if I have data and I'm just asking you to find the weights that best fit the data, this is NP hard, even for a tiny network with just 2 hidden units, the kind of smallest type of network you'd imagine. But then you can say, well, what if I'm allowing you to use a larger network? What if I'm assuming the data is generated by a small network? I mean, you can fit it with a small network, and I'm allowing you to use a larger network or do all kinds of other tricks. Unfortunately, we have very strong negative results also there. And when I say we, in most of this talk, definitely in this slide, it's the community. It's not our group specifically. Okay? So we have a lot of negative results there. And these negative results tell us that there's no efficient learning algorithm for learning neural networks. So what does that mean? That means that even if you promise me that there exists a tiny network, a network with a single hidden layer and some fairly small number of units that exactly fits the labels. So the labels are exactly generated from this network. There's no error at all. Okay? The network is small. And even if you allow me to use a much larger network or anything then there's no algorithm that is guaranteed to learn just based on the assumption that there exists a small network that exactly fits the data. Okay? Right. So this is a very disappointing. Right? It means that neural networks do not learn. Now, I just told you that you cannot learn with deep networks. I mean, of course, I'm assuming that many of you, and if this was, if I could see you, I would maybe ask you to raise your hands if you've ever trained a neural network and it actually succeeded and learned whatever it is that you wanted it to learn. And I'm sure many of you have done this. So what's going on here? On one hand, I told you that provably you cannot learn with neural networks. On the other hand, many of you learn with neural networks all the time, and we have lots of amazing empirical success with neural networks. So what's going on here? The thing is that this result is, of course, a worst case result. What this means is that there is no efficient method that can learn anything representable with a small neural network. Okay? Okay? But the thing is that the things that we want to learn are not just anything. It seems that the phenomena that we do want to learn, the type of problems we want to learn, presumably have some kind of property that allow them to be learnable. So they'd have what I would call some magic property, okay? That under this magic property, local search can actually succeed in training a neural network. And what I would say is the biggest problem in deep learning is identifying what is this magic property. What is this magic property that makes a problem actually learnable by local search or gradient descent on a neural net? Okay? And I would argue that even after working and trying to understand deep learning for several years now, roughly speaking, we still have no idea what this magic property is. We are starting to maybe have some inkling, and maybe I'll get to it later, but we really don't know. We only know what this magic property is not. So what we know is this magic property is not that the problem is representable with a small neural network. Because as I said, this is provably not sufficient to be able to be learnable by a neural network. So what this means is, if we're looking for an explanation of why do we succeed in learning with neural networks, why does deep learning work, I have no idea what the correct answer is, but I know what the incorrect answer is. The incorrect answer is that neural networks capture the phenomena that I'm trying to capturing very well, right? So if you ask a vision person or yourself, why do neural networks work? And the answer is neural networks work well because they really capture visual phenomena. You can many visual phenomena you can express in terms of low-level features and mid-level features and high-level features. And so neural networks really capture visual phenomena. What this answers is this question, okay? It tells us that there exists, that you can express your problem with a small neural network. But as we said, that is provably not sufficient for being able to actually train the neural network. And so that is, and in fact, as we said, we don't really need that explanation because we know that anything we can represent with a small neural network. Okay? So that provides almost no answer towards the question of why do deep networks work, and why does deep net learning work? How can we succeed learning by training a neural network with local search, even though in the worst case we can't do that? So what is this magic property? So as I said, I don't know, and in fact, what we're going to talk about today is a bit different. So if you asked me about 5 years ago, 6 years ago now, what is it we know and don't know about deep learning? What should we study? I would say, well, we completely understand the issue of the capacity of neural networks. We have classic results that tell us exactly the capacity scale with a number of units. We also understand the expressive power very well. Both we have lots of understanding of specific phenomena that are captured by small neural networks, and we have these kind of universal results. And the only thing we don't understand is computation. Why does local search work? And in fact, we try to understand, when does local search succeed? But what I'll try to show you in the next 40 minutes or so is that the situation is actually more complex. That not only do we not understand the computational aspects, but actually, we also don't understand the expressive power aspects and the capacity aspects. And this really started from an experiment we did about 6 or 7 years ago. And what we did is the following. So we did a very simple experiment. This is due to this is with Benem Neshabur and Ryota Tomioka. And we trained on several different data sets. We trained neural networks of different increasing size. Okay, and what I'm showing here on the x-axis is the number of fitted units, the size of the network. And I should emphasize that every point here is an independent training. This isn't that, the x-axis is not time along training. We didn't start with 4 and gradually increased it. We trained with 4 units, then trained from scratch with 8 units, and so forth. Okay? And what we're tracking is what's the training error for training this network and what's the test error at convergence. And I should say that the way we train it is just by gradient descent on the training error. Okay? We just try to fit the training, fit the data, fit the network to the data. Okay, so what do we see here? Well, the training error decreases. Okay? That's not surprising because the bigger the network, the more expressive it is. I mean, the easier it is to fit the data. And we see here that with the 64 units, we already find a complete fit for the data. So you can get 0 training error. And any number of units bigger than that, we still get 0 training error, of course. The question is, how does the test error behave? So initially, the test error goes down. And this is not surprising. We're getting better and better fit for the data. The network fits the data better. It's perhaps not surprising that it also fits the test data better, generalize as well, and we have some gap here. It's fine. But what happens beyond this point? So what we would expect based on our classic understanding is at this point, the test error should start increasing because we're not getting any better fit for the data. Okay? So our approximation error is not improving. On the other hand, the network becomes more and more and more complex. So remember, we said that our generalization ability, at least according to our classic understanding, is related to the size of the network. And so it should start becoming harder and harder to actually generalize. The estimation error, if you wish, would start being larger, and we should start overfitting. And in fact, with 1,000 units in this specific example, we already have more network parameters than data points, and so we can't expect any form of generalization. I mean, this should just be way, the test error here should be just through the sky. Okay, so this is what we expected, but what we actually see is quite different. Okay? So what we see is not only does the test error not increase, but it actually continues decreasing. Okay? So we actually get smaller and smaller test error. So this is very strange. Why? So there's kind of 2 questions we should ask ourselves here. Why is the test error here not shooting up through the roof? Why is it that we train a network with 1,000, 2,000, 4,000 units, and we have many, many more parameters than training points? How come we're generalizing at all? And it seems that there must be some other complexity measure at play here that's preventing us from overfitting and ensuring generalization. And moreover, not only are we generalizing, but we keep generalizing better and better, even though the number of units increase, right? So the fit isn't getting better here, but the generalization error is getting better. So maybe actually the complexity of the network, which determines how well we generalize, is not increasing, but decreasing. So maybe it's determined by something other than number of fitted units. Okay, so let's look at it.
Quick question, Nadi.
Yeah,
so
sure.
How many data samples are used in this? So I guess it's not given in this figure, right?
It's not given in this figure, and I'm embarrassed to say that I actually don't remember at this point.
Okay, that's fine.
But you can look at it in a paper. I think this is actually a reasonably small. This is either MNIST or CFAR. So this is MNIST, I think, based on the errors. So I think this is just trained in full MNIST data. So several tens of thousands.
So I guess sometimes I've seen pictures where people talk about the error going down and then going up, and the number of hidden units is equal to the number of samples and then goes down again. So people talk about the double descent curve, which I'm sure you're
right.
So how come
right. So right.
Yeah.
So the reason it doesn't. Okay. So you can actually see it. So if in some of our plots, actually, you do see a bit of a double descent. You see it. This is where you would kind of see this double descent. And if you look at some of our other plots, there's a bit more pronounced double descent.
Okay.
We did not. So I should say that when we looked at this back in 2014, I mean, this was, we didn't even think about that, and so we completely missed the double descent in our plots. I mean, we were more concerned about what's going on here, and kind of missed the fact that over here in some plots we see a double descent. And after the double descent phenomena was pointed out, then you can go back to our plots and see that you can also see it there, even though again we did not notice it at the time. Okay, but yeah, that's an excellent question. Okay, so right, so what's going on? Okay, so what's going on here? So let's look specifically at what's going on with 1,000 units. So as I said, if I train a network with 1,000 hidden units, we get some to some global minima of the training error, and it has pretty small test error. It has test error for about something like 1.5% test error. Okay. Now I know that this is, I mean, I'm doing on local search, but I know this is a global minima because global minima of the training error, because the training error is 0, so it's definitely a global minima. The thing is that this is not the only global minima of the training error. Okay? As I said, this network has many more training parameters than many more parameters than training examples, and so actually there are many global minima. There are many settings of the parameters that give us 0 training error. Okay? So what I'm going to plot here is a bunch more global minima. So each one of these points corresponds to a different global minima of the training objective. Okay? And as we can see, the global minima that we found actually generalizes very well, but many other global minima generalize horribly. They have test error that's even close to 1, right? So what's going on here? What's special about the global minima that we found? Okay? And that actually allows generalization. And for that, we can go back to actually intuition that Peter Bartlett had more than 2 decades ago, in saying that really maybe what's going on here is that the relevant complexity parameter is not the number of hidden units, but some other complexity parameters, such as the weight, the size of the weights, or the magnitude of the weights, okay, some kind of norm. And indeed, what I'm plotting here, oops, it's not showing, but what I'm plotting on this axis is a norm. Okay, and so indeed we see that these global minima are maybe not generalizing well because they have high norm, whereas this global minima is generalizing well, but it has a small norm. Okay, so maybe what we're doing here actually is finding a small norm global minima, a small norm solution, and we're generalizing not because number of units is small, but because the norm is small. Okay? And now the question is which norm? Okay? There are many different norms I can plot here, and actually I see the question. I'm going to answer it in a second. The question is which norm are we showing here? And I can tell you that if we plotted, for example, the Frobenius norm on the x-axis here, we would not get such a nice graph. Okay, so we have to choose the norm very carefully. The norm we have here I'm not going to go into the details of what this means, but it's a particular norm of the weights, which we call the path norm. Okay? So let me just answer a question. Somebody asked, how did I actually get these bad global minima? So it turns out it's much harder to get bad global minima than it is to get good global minima. Okay, so first of all, and this is something that's going to come up again, what do I mean by good global minima and bad global minima? All of these are global minima of the training objective. So all of them are global minima. And when they say good and bad, I mean, some of the global minima seem to generalize well and some do not. It's actually much harder to find the global minima that do not generalize well. What we did here in order to find them is actually in our optimization procedure, we intentionally cheated and also included a term when we optimized that tried to increase the test error. So we are finding a global minima because we are minimizing the training error, but we're minimizing the training error while intentionally trying to find the largest test error that we can. Okay, so that's actually how we got these, which turned out to be actually kind of tricky numerically. Okay, I think hope that answers question.
There's a
Let me just.
lighthearted question. Apparently, what they want to know what's your background
Oh,
is.
okay. So I'm. I can answer that question as well. Maybe I should have started there. I'm actually now in sabbatical at the Weizmann Institute, and this is a picture of the now defunct upright linear particle accelerator in the physics building right next door here at the Weizmann Institute.
Thanks.
Okay. Okay. Right. Okay. So where were we? Okay. So what we're seeing here is that maybe the reason we're generalizing is, again, not because of the number of units, but because of some other complexity measure. But the first question we should ask ourselves then, if really the reason we're generalizing is not because the number of units is small, but because of some norm is small, the first question we should ask is, what is this complexity measure? What is this norm? You know, is it the Frobenius norm? Is it the path norm? I can tell you it's not either one of them. It's some other maybe complexity measure that we're starting to have a sense of what it is, but we have still not fully uncovered. But the second question is, how come whatever this complexity measure it is, how come the algorithm is actually minimizing it? Okay, so again, what we told the algorithm to do is just minimize the training error. All we did is gradient descent on the training error. Okay? Any one of these red dots would be a perfectly valid answer to the algorithm. I could not complain to the algorithm if it returned to me this point. It is a global minimum of the objective. Nevertheless, the algorithm seems to implicitly be preferring not just any global minima, but a global minima that actually minimizes some complexity measure. Okay, how is this happening in the algorithm? And that also means that if we're saying that all our generalization ability comes from this complexity measure, not from the model itself or number of units, by this implicit complexity measure, and this complexity measure is induced by the optimization algorithm implicitly, then that means that if we change our optimization algorithm, we're also going to change the generalization properties of the network. And indeed, we see this. Here are some examples. So first example, we compared standard SGD and path SGD, which is approximate steepest descent with respect to this path norm. It doesn't matter at all what it is. The only point here is there are two optimization algorithms, the red algorithm and the blue algorithm. Okay? Both of these find the global minima. How do I know the global minima? This is the training objective, the cross-entropy training objective. Both of them find a zero error solution in both cases. And so both of them return the global minima. They're doing exactly what they are supposed to in terms of optimization algorithm. Maybe the blue algorithm is a bit faster. That's less important. But when we go to the test error, we see that the global minima the blue algorithm finds is a much better global minima than the global minima the red algorithm finds. Again, when I say a better global minima, I'm being really unfair to the algorithm. The algorithm was told to find a global minima, find the minima, and it's doing this. But in terms of this generalization ability that the algorithm was not told to optimize and has no idea about, the blue algorithm is doing a better job. So it seems that the blue algorithm has a better implicit bias. Whatever it is, complexity measure it's implicitly minimizing might be a better complexity measure than whatever the red algorithm is minimizing. You can see it just with dropout. This is another example. SGD versus Adam. Some of you might be familiar with Adam, which is SGD with both a momentum term and some feature-wise adaptivity or parameter-wise adaptivity. It doesn't really matter if you're not. Just think of it again as a red algorithm and a blue algorithm. And what we see here is the optimization curves. And again, both algorithms are going to, eventually, they're going to get to the same point. They find a minimum of the training objective. And the red algorithm is actually even doing a better job, and it's faster. But when we go to the generalization errors, we see that the red algorithm, which is Adam in this case, the minima that it's finding is actually a bad minima. It generalizes poorly, whereas the minima the blue algorithm finds, it seems to have a better implicit bias, and it's generalizing better. Okay? So the picture we're trying to see here is that what's going on here is the different algorithms have different biases into which optimum they prefer. And really what I would argue is that all the inductive bias of learning, everything that determines why we generalize and what are we going to generalize and what we're actually learning, comes from this implicit bias. And so different algorithms have different generalization properties. In order to understand and what we're doing in deep learning, we really have to understand optimization algorithms, not just as finding a global minima, but understanding which global minima. So maybe a way to think about it is as follows. So remember that the problems we're looking at are highly overparameterized problems, right? They have many more parameters than data points. And this is generally true for many deep learning tasks. And in that case, there are many global minima. The global minima of zero-error solutions. So think of these zero-error solutions as the oceans. There are many solutions at sea level, at level 0. Okay? And you're going to start optimizing, not for zero solutions, so you're going to start optimizing on some kind of hill. Okay? And then you're going to go down from the hill. Okay? And the question is, where are you going to get? Okay, great. So you're going to get, at least if optimization succeeds, and this is again a different question, you're going to get to a zero-error solution. But the question is, which zero-error solution are you going to get to? You're not going to get to a zero-error solution that's in the middle of the ocean. You're going to get to a zero-error solution on the beach, right? Because you're going to get there and then stop. But which beach? Okay. So if you start optimizing in Berkeley, then you're going to go down, and you're probably going to get to the San Francisco Bay and stop there. Okay. If you start optimizing in the hills above Boston, again, you're going to go down, and you're going to get somewhere in the Atlantic or Charles or something like that. The interesting question is what happens when you start optimizing in Urbana. Okay. So Urbana, from what I remember, is pretty flat. Okay? And you can get, I know that at least now Chicago, which is not quite as flat as Urbana, and even in Chicago, it's so flat that the rivers flow backwards, right? So you can really get to anywhere. And now it's really a question of which direction does your algorithm prefer moving. If your algorithm kind of prefers going south, you might find yourself in the Gulf of Mexico. If your algorithm sort of prefers going north, you might find yourself in the Hudson Bay. Okay? You might even go east and manage finding a way to the eastern seaboard and in the Atlantic Ocean. Okay? And where you're going to end up is going to determine by kind of the geometry of your optimization algorithm, which kind of directions it prefers going in. And the thing is that in high dimensions, pretty much every place is like Urbana, because in every place there's lots of flat directions, but lots of directions you can go to, and lots of opportunities for descent. Okay? And so everything where you're going to end up is determined by the geometry of optimization algorithm. Now, what I'm arguing actually, just a second, I see a question here. Do you expect that SPM with extensive hyperparameter tuning process could match a performance to HDD path method? Okay, so there's a question here if you tune things, can you match the performance of the path SGD? Yes, even if you just add batch norm, that already changes things, and usually better, usually about the same. Sometimes path norm is a bit better. The point here that I was trying to make was not so much to show what's the best method, but rather that just by changing my optimization method, I can get very different solutions. If I changed hyperparameters, I could get to different solutions. And again, changing just the fact that if we change hyperparameters, I get to global minima, but a different global minima with different properties, already kind of makes the point that I want to make, which is what's important is not the global minima that I get to, but the changing the hyperparameters. Actually, what they actually change is the implicit bias of the algorithm in which global minima I get to. Okay, so I hope that answers the question. Okay, so let's get back to here. And what I'd argue is that actually the situation is that everything is determined just by the implicit bias of the algorithm, because actually our networks are so big that essentially they represent all functions. And so really we're back in the situation we said that that initially we dismissed, that neural networks can approximate all functions, right? If the size of the network is large enough, you can really capture all functions. So maybe we should be thinking of neural networks as universal approximators that can approximate all functions. But if it can approximate all functions, that means that the model itself does not provide any capacity control, right? It's just the space of all functions. Okay, so what's special here, the whole reason we generalize is because we're searching in the space of all functions. And it's very easy to find the global minima in the space of all functions. You can just fit the data and you memorize the data is a global minima of the error in the space of all functions. But we're not going to get to that global minima. The search dynamics in the space of all functions, okay, is such that it's going to find a particularly global minima that maybe is low complexity in some other measure. And so all the inductive bias, all of it is coming just from the search algorithm, just from the search geometry in which algorithm I use, because the model class itself is not constraining me at all. It doesn't actually provide anything in terms of learning. So really that means that if we look at a typical learning paper, then we focus a lot on the model and the model class, right? So say why this model is good, why it can really model reality, it can capture lots of things. And how do we learn? Well, we learn just by minimizing the training error in our model class. And how do we do this argument? We just write in this argument. I mean, we at this point, we just kind of take for granted that it's just an argument. We minimize it somehow. Okay. And then so I see there's a question. I'm going to answer it in a second. And so really, what I would argue is that everything that determines the learning is actually hidden in this how do we do the optimization, and the details of optimization, which are sometimes maybe even hidden in the appendix or in the source code or something. This is what determines everything, and this is what we have to determine. Let me just see. There's a question here. Let me read the question. There's some work showing the training error can go to 0 if we assign labels randomly. I imagine that I can adversarially randomize the labels so the training data goes to 0, but all global minima are very bad regardless of network size. I'm a bit okay. So first of all, the question is: does the magic property involve the data as well? Can people actually see the questions? I'm not sure if only I can see the question or if anybody can see. Everybody can see the question.
I think people should be able to see the question, but it might be a good idea for you to read it just in case.
Right. Okay. Great. So the question here points out that since the networks have so high capacity, then I can fit even random labels, right? So this is not surprising. Again, the networks that we use have more parameters than number of examples. We're optimizing the space of all functions. I can fit everything, even random labels. Okay. So does that mean that the magic property we talked about before involves also the data? So first of all, the magic property that I'm pretty sure involves also the data. I mean, it involves it involves or rather, I'm not sure. It depends what you mean by data. It involves the source distribution, the reality, the joint distribution over x and y. Once I use random labels, that means that I have a different joint distribution over x and y. And even if I can get 0 training error, I cannot hope to generalize. And there's no way of generalizing because the base error is trivial. It's half or whatever. So that's that aspect. I think there was maybe another part of this question, but now it disappeared, so I don't remember it. If that didn't answer your question, you're welcome to ask the question again. I can maybe answer. Okay, so I mean, let me maybe try to show you with a simple example how we can, how indeed we can rely just on the implicit bias in order to learn without relying on the model class at all. And I'm seeing that. Maybe hurry up a bit. Okay, and this is instead of looking at deep learning, which is rather complicated, look at something that I've been working on for a long time and I actually know something about it and I sort of understand, which is matrix completion with matrix completion and matrix vectorization. So the problem we're going to look at is just the problem of matrix completion as a partially observed matrix, and I want to complete the unobserved entry. So how will I do that? I can set up as optimization problem. I just find the matrix X that minimizes the error on the observed entries. So this is, of course, a completely stupid optimization problem. It's completely nonsensical. It doesn't make any sense. It's very easy to solve, but it has lots of global minima. Okay? And many of those global minima are worthless. Like, how can I get a global minima here? For example, I can complete the observed entries and put 0 everywhere else. Or I can complete the observed entries and put 63 everywhere else. Or I can do lots of other strange things. There are many global minima, and many of them do not generalize well, just like we saw before. Okay? So what I'm going to do is I'm going to take but at the very least, this is a simple convex optimization problem that's easy to solve. So what I'm going to do is I'm going to take the deep learning approach. I'm going to take this convex optimization problem that already has too many parameters, has more parameters than data points, and I'm going to write it as an equivalent problem, but that has many more parameters and is non-convex. So then where I'm going to write it, I was going to write x as u times v. U and v are full dimensional, so if x is n by n, and both u and v are n by n, so I have twice as many parameters. Okay? In every matrix x, I can represent as u times v. For example, I can write as x times identity. Okay? So I didn't here put any restrictions on x. I'm just changing the parameterization. Okay? And now I'm going to look at the problem of minimizing the same objective with respect to u and v. These are now my parameters. So this is the same optimization problem. I didn't really change the optimization problem at all. But let's see what happens when you do gradient descent with respect to x as opposed to gradient descent with respect to u and v. So these are two different optimization algorithms for the same problem. Okay? So in both cases, I find a global minima of the training error. So these are you don't see them because they're 0. Okay? But what's interesting is the test error is different. So if I do gradient descent on x, my test error is trivial. What I'm going to do is I'm going to just fit the 30% of observed entries and all of the 70% of unobserved entries. I'm going to get trivial error on them. Okay? But if I do gradient descent on u and v, then actually the test error is not so bad. So I managed learning here. Now I should say that this data was generated from an approximately low rank metrics, so I have hope of learning. But there's nothing in the algorithm that actually tells me to look for such matrices, right? So the algorithm kind of, even though there are many global minima, magically actually found a pretty decent global minima. And let's tweak the training algorithm even some more. So this is the results with gradient descent with exact line search. If instead I switch to gradient descent with a very small step size, then optimization is actually worse here. It's going to take me much more time to optimize, but I found a much better global minima. So again, what does it mean much better? I found a global minima that generalizes much better. Okay? And so what's going on here? So I'd argue that this is exactly the phenomena we're seeing in deep learning. Okay? The problem doesn't make sense. It has lots of global minima. I can fit random labels here, right? I could also be able to fit random labels. But because of the choice optimization algorithm, the implicit bias actually guides me to a good solution. Now, if I tweak the optimization algorithm, I can change my implicit bias and I can even improve it. But I should point out that the main phenomena here is not this difference between gradient descent with exact line search and gradient descent with small step size. I mean, this is a small difference. The big phenomena is how come any of these are learning in the first place. It's the gap between this good test error and this horrible test error that I get with a different gradient descent and different parameterization. Okay? And in this case, we kind of sort of understand what's going on. So what's going on here is that in some sense, there's a complexity measure that's being minimized. Usually we conjecture that the complexity measure being minimized here is the nuclear norm. It turns out to be true in some, we proved it in some special cases. It's true in some other special cases, basically when recovery is possible. It's not actually always true, and we still don't understand exactly what's going on here. And again, the details here, I mean, I'm not going to go to any of the details here. The point is the behavior is exactly this behavior that we have for deep learning, and we can now understand why we actually generalize, understand rigorously how come just the change of optimization algorithm allows us to generalize, partially by identifying a complexity measure that's being minimized. Okay, so again, the name of the game here is trying to identify, relate an optimization algorithm to the complexity measure being minimized. Okay? So when we first started looking at this, I thought, okay, the simplest thing to look at is least square problems. Okay, least square problems are always the simplest. And in fact, for gradient descent on a linear least square problem, we can easily identify this implicit bias. Right? So if you minimize a underdetermined least square problem, you'll always go to not just any minimizer, but the minimum norm minimizer. This is what's going on. But let's go to more complex problems. So we already talked about metric factorization. And it turns out that, it's kind of the nuclear norm, maybe in some cases, very special cases, but it's not in general. And also only, if the step size is almost 0 and you initialize close to 0, 0 is a saddle point, it's a miss. Okay? We also mentioned Adagrad before. So Adagrad is somewhat related to minimizing the L-infinity norm, but not always, and depends on a lot of other things. And again, it's a miss. And we actually we should have known it's going to be a miss, because another example is coordinate descent. In coordinate descent, you can also use steepest descent with respect to L1 norm. You'd imagine it'll be related to the L1 norm. And we know it's related to the L1 norm in the same sense that Lars is related to Lasso. So Lars is roughly following the, doing optimization with coordinate descent, but they're only kind of related. It's not the same. So it looks at in this case, actually, the least square squared loss objective turns out to be more complicated. But luckily, that's not actually a loss function that's usually used in deep learning. The loss function maybe that's more commonly used is the cross entropy or logistic loss. Okay, so let's look at what happens when you minimize logistic loss. So again, look at the same type of problem, a linear prediction problem. Minimizing logistic loss, you can think of it as just the simplest neural network you imagine, a neural network with a single unit, no hidden units, just a single unit network. And what's going to happen here, so we're going to optimize, we're going to get to go towards a zero solution. But again, the question is which one. So the interesting case is what happens when the data is linearly separable. Okay, and now I optimize with gradient descent, and where is gradient descent going to converge? So this is actually a trick question. Gradient descent is actually not going to converge here. Gradient descent is going to diverge, because the only way to drive logistic loss or cross entropy loss to zero is to drive your weight vector to infinity. But that's fine. The weight vector is going to go to infinity, but it's still going to define a finite separating hyperplane. So it's going to go to infinity in some direction that separates the data. But the thing is, there are many directions to separate the data. Okay? The question is, which of these directions that separate the data are we actually going to converge to? It turns out, I see I'm running out of time, so I'm not going to let you guess. It turns out that what's happening here when you train a single unit, so a logistic regression model with gradient descent, then the direction you're going to converge to is exactly the hard margin SVM direction, the direction that minimizes the L2 margin or maximizes the L2 margin or minimizes the L2 norm subject to a margin constraint. So you're implicitly solving a hard margin SVM problem. And I want to emphasize that all I'm doing here is gradient descent and logistic loss. I do not have a notion of margin in here. I do not have the L2 norm in there. I do not have the hinge loss in there. It's just gradient descent and logistic loss. And the fact that I'm getting a hard margin SVM is coming just from the optimization algorithm. If you use a different optimization algorithm, I'd actually get a different implicit bias. Okay, let me skip this because see. So it turns out that that logistic loss or cross entropy loss is indeed much easier to analyze. We can characterize what happens again with a single unit. I get the hard margin SVM. We can also see what happens with multiple units. And as I said, if we change the optimization algorithm, we can also characterize what happens. So if we do steepest descent instead of gradient descent, instead of getting the maximum Euclidean margin, I get kind of the maximum L1 margin solution. And I can also analyze the metrics factorization problem we get before. And in this case, we can indeed say that what we're doing is exactly implicit in minimizing the nuclear. So we have actually a much better understanding in the case of logistic loss. Let me skip this. Okay, so this is just a single unit, but we want to get to more complicated networks. And let's try to get a sense and see how far we can go with this notion of implicit bias. So we can ask, we'll stick to linear networks. So we're going to talk only about networks where all the units are linear. In this case, we can ask, does this give me a more interesting implicit bias? So what's going on here is if I have a linear network, it's just a strange parameterization of a linear predictor. So at the end of the day, I'm just learning a linear predictor, but I'm learning it with a particular parameterization. We already saw before. So I think I'm going to, since I'm running low on time and I had already quite a few questions, I think I'm going to try to, unless there are very burning questions, try to finish the talk at this point. So I'll answer the questions at the end. And so it's a different parameterization of linear predictors, but we already saw before that just changing the parameterizations, going from a matrix to a product of matrices can change things. What happens here? The answer is pretty boring. For a fully connected linear network, if we do gradients in the parameters, we still get to a hard margin SVM solution. But things become more interesting if we look at linear convolutional networks, right? So these are networks where each layer implements, in this case, a 1D convolution, okay? And the activation functions are still linear. So this is still just implementing a linear predictor. It's a fancy parameterization of a linear predictor. What happens when we train it with gradient descent? So again, the optimization problem here is exactly the same. We're just solving logistic regression, but we're solving it with this bizarre overparameterization. And now we get something very interesting. If we train a linear convolutional network with gradient descent, instead of getting the max Euclidean margin, we're getting max margin with respect to an L1 norm in the frequency domain. So that means that we're getting sparsity in the frequency domain. And if you go to deeper networks, so this is for depth 2, if we go to deeper networks, then what we get is even more sparsity inducing penalties. We roughly minimize this bridge penalty, this 2 over depth quasi norm. So something that gets even sparser and sparser as we go deeper. Okay, so just to visualize this is what we get for this. This is how the predictor looks like. If we train a fully connected network, if we switch to a convolutional network with depth 2, we already get some kind of sparsity in this frequency domain. It looks like a sinusoid. And with depth 5, we get almost a perfect sinusoid. Now, I want to emphasize that all of these solutions are valid global minima. All of them are separators for the data. Okay? But the fact that we changed the architecture here made the implicit bias different, made the geometry of the optimization different, and so guided us to different minima. In particular, with a deep convolutional network, we get some sparsity in the frequency domain. Okay, so we already talked about 2 examples, which is matrix factorization in linear convolutional networks. And in both of these cases, I would argue that we have a representation of all functions. In the case of matrix factorization, this all functions was all matrices, right? We did not constrain the set of matrices, but just by optimizing in a particular way, we got a particular and very rich inductive bias. And then we turn to linear convolutional networks. Now all functions is all linear functions, all linear predictors. And again, inside the space of all linear predictors, think of this as very high dimensional linear predictors, we got very special inductive bias, and this is sparsity in the frequency domain. But you can also see this really with all functions, not just all matrices or all linear functions. So let's look at infinite width ReLU networks. So infinite width ReLU networks are really a parameterization of all functions. You can, as we said before, you can approximate any function arbitrarily well within infinite width ReLU networks. So we have here a parameterization of all functions. And the question is, what happens if we train this with gradient descent? So again, we're going to fit the data, but there are many functions that fit the data. Which functions are we going to prefer? And it turns out we can exactly know the answer. So for univariate functions, it's also easy to write the answer. What we're going to be doing is up to some correction term that we can specify exactly. We're going to be minimizing this second order total variation penalty on the function. So we're going to find the function that fits the data and minimizes this integral of the second derivative of the function. So some kind of smoothness penalty on the functions. Now again, we did not encode this into our objective. We're just fitting the data. But the implicit bias of training an infinite width ReLU network induces this very natural sparsity inducing smoothness type penalty. So this is for univariate functions. We also have a generalization for multivariate functions. Now this absolute value of the second derivative becomes some iterative Laplacian of the Radon transform. Again, we can specify this exactly. So what's going on here is that really when we talk about inductive bias, we have to separate between what's going on in the parameter space and what's going on in function space. Okay? And the architecture defines some mapping between parameter space and function space. And what we see here that maybe in parameter space, the inductive bias is, has a relatively easy shape. But once we go to function space, this maps to very rich inductive bias. And so it's not that the architecture doesn't matter. I said before that the model class doesn't matter. I hold to the fact that the model class doesn't matter. But the architecture does, because it's not that the architecture, in my view, determines the model class, but rather the architecture defines how the local search geometry in parameter space looks like in function space. And this geometry of the search and function space is exactly what determines the inductive bias and determine what's going on. Okay, let me wrap up. Skip this, and let's finish where we started. And so we said at the beginning that we understood the expressive power and we understood the capacity, but we didn't understand the computational aspects. I would argue that actually we don't understand anything. Because if we say that generalization ability doesn't come from the number of units, it comes from some underlying complexity measure, Then also when we talk about capacity and generalization ability, we have to talk about capacity and generalization ability of networks that have small norm or complexity or whatnot. We don't even know what this norm is, and so we definitely don't yet have a handle on understanding the capacity or the sample complexity. Also, when we talk about expressive power, now we said that it's not about saying what can we fit with a neural net with any neural network. As we said at the beginning, we said what can we fit with a small neural network. And now we see that what we should really ask is not what we should fit with a small neural network, but what can we fit with a neural network that's maybe large, but it has small complexity. But again, I don't even know complexity under what. So actually, we tried to take a step forward and we got 2 steps back. We actually are back at trying to understand not only the computational aspects, but also statistical aspects of the sample complexity and the expressive power. Okay, I think I'm a bit over time. Let me end here. And if we still do have a few more minutes, I'll be happy to take additional questions.
Thank you, Nadi. That was a wonderful talk. That was covered a lot of ground and was gave everybody a great sense of what this topic is about. I would, since I think we're out of time, and there's a talk by Kristen Grauman actually at Illinois starting right now. So if you have any questions, please email Nadi directly. And also, I guess somebody's asking for slides. I guess he has promised to give us the slides early next week, and we'll put them up on our website. Yeah. Okay. Thank you so much. That was a wonderful talk.
Thank you very much.
Great talk.
Okay.
Bye.
Thank you. Bye.